Welcome to a video on basic BJT differential amplifiers. In this video we will have a look at the DC analysis, the common mode input range, the parameters that we will get, some configurations of this amplifier, then the differential amplifier parameters, gain, input impedance, etc. The common mode parameters, and then the output offset voltages and currents. And then lastly add some simulations of the problems. Okay, so in this video the transistors we use will have a beta value of 200, VBE of 0.7, a current source of 1 milliampere, rail voltages of 10 volts. The minimum current across the current source for it to operate properly is 1.6 volts. Collector resistors of 10 kilo ohm. If we include emitter resistors later on, they would be 100 ohm each. The impedance of a current source is 100 kilo ohms, and if we later go over to resistor biasing, instead of using a current source, we will use 8.2 kilo ohm resistors. Right. So first we will have a look at the DC analysis of one of these amplifiers. So if we have a current source down here at 1 milliampere and we ground the two inputs, the current will divide equivalently between the two half circuits, and that means that we will have 500 microamperes sitting on each side. So in maths, we have the emitter current down here being driven by a current source, so the two emitter currents will be equivalent, and with a large beta value our collector currents will be equivalent. So large enough beta, don't care about the little bit that gets lost here at the base. Right, if our transistors are matched, it means our VBEs will be exactly the same, and our collector our collector voltages, so one here and one here, must be exactly the same. So VCC minus ICRC is 5 volts. If we place a resistor here as our load, the DC voltages will cancel and only the AC will remain as long as these two voltages are equivalent. Okay, at this point right here, our VE is minus 0.7 volts, and that is roughly the DC for one of these amplifiers. Our common mode input range, so our maximum is our VCC subtract our voltage drop across the collector resistor plus a 0.4 volt right here. Now that is when our transistor are leaving the active region and entering saturation, and that is at roughly 0.4 volts. So our maximum common mode voltage is 5.4 volts, and our minimum is, when we are looking at the loop down here, is VBE plus our current source drop plus our VEE is minus 7.7 volts. Right, so if both sides of this amplifier is biased to the same current, that means that our transconductance for each transistor will be the same, the input resistance will be the same, the output resistance will be the same, and that is as long as our beta values are exactly the same. So with our 500 microampere bias, our transconductances will be 10 milliampere, and our R pi will be at 10 kilo ohms, and we didn't give a early voltage, so this will be infinite in our problems, but if it's given, they will also be exactly the same. Note that we can add small emitter resistors, and small emitter resistors in one of these configurations will yield a larger input impedance. It will yield a larger input range for your amplifier to keep it more linear. But the downside is it will reduce your amplifier gain. So here is our two configurations with and without small emitter resistors added. So if we use this input as our non-inverting, this will be our non-inverting output, and this will be our inverting output. So from our MOSFET configurations to our BJT configurations, these definitions are still the same. So onward from here, we will look at two configurations, and that is with and without the emitter resistor, and we will also be looking at fully differential and single-ended outputs for these amplifiers. So first off, if our amplifier, we do the small signal parameters, our DC sources will switch off, our current sources will become open circuits, and our amplifier will look something like this. And it looks again like two common emitter amplifiers. Right, so when we are looking at both inputs simultaneously, or we can do it just by looking at one at a time, we have a differential input impedance. With the MOSFETs, this is infinite, but with BJTs, it is a little bit different. So we can approach this in two ways, and that is either viewing one transistor looking in to the ground over here, and the other one to the ground over here. That is one philosophy, or the other philosophy is grounding it and looking right through to the ground on this side. Okay, so looking at the first philosophy is having two different inputs and having this as a ground. So looking into this transistor, you will be seeing R pi, and looking into this transistor this side, you will be seeing R pi. Okay, so the input impedance is typically 2 times R pi for these amplifiers. The second philosophy is the one that is depicted here, is when we're looking in from this side and say this side is grounded, we are seeing R pi looking in. Right, and anything beyond this point must be multiplied by beta plus 1, so it will appear larger. So looking into this transistor right here, we see its small re, and a small re multiplied by beta plus 1 is R pi. So if these two transistors are matching, we have R pi 1 plus beta plus 1 times Re2, which is 2 times R pi. Okay, so our R pi here is 10 kilo ohms. So for this amplifier, the input impedance will be 20 kilo ohms, whether we're viewing from one input only or from both inputs simultaneously, we will be seeing 20 kilo ohms. Even with a single ended output, we will be seeing 20 kilo ohms. If we're just using one input or both, it will remain 20 kilo ohms. Right. The output impedance, However, when looking at this differentially is 2 times RC, and if we are viewing it single-ended is 1 times RC. So it is 20 kilo ohms for fully differential and 10 kilo ohms for single-ended. If we were to add 2 small emitter resistors, we can follow the same philosophy by viewing both inputs simultaneously, and thus we will have double um, what we see on one side, or we can view from one side to the other side using the one input as a ground. So looking in, we see R pi, we see beta times RE, we see beta times RE again, and we see beta plus 1 times small re 2. Right, so our input differential increases with small emitter resistors. So we had this as 100 ohms in one of the earlier slides. So our input impedance will increase to 60.2 kilo ohms with this added emitter resistors. Note, nothing changes with our output impedance, whether it be differential or single-ended. Right, the next step is the differential gain. So if we insert plus VID over 2 and minus VID over 2 here and find our two output voltages, we will find that it is GM times RC on both sides, and doing the subtraction V out 2 minus V out 1, we get GM RC as our gain. So our fully differential gain is 200 volts per volts. If we are not neglecting our output impedance of our transistor, we need to add it as a parallel to our collector resistors. And our single-ended, again, when we're only looking at one output, is half the gain, so 100 volts per volts. With added emitter resistors, we will have some degeneration going on. So our maximum gain over 1 plus GMRE, and you will find that our differential gain then is GMRC over 1 plus GMRE, and that will be 67 volts per volts with 100 ohm resistors at the emitters. And if we do this only single-endedly, we will only have half the gain available, so 33 volts per volts. Looking at our common mode, so our the case where both sides have the same input, the rises and falls will be the same, so our current source gets taken away from this equation and we have our emitter resistor present. We can split our signal or our common mode amplifier into two, so we have 2 times REE sitting here at the current source, and 2 times REE in parallel with 2 times REE is just REE. Note that with the degeneration resistor, the 2 needs to be added, but in general, the emitter resistor is much smaller than the resistance of the current source. So to make your maths easy, you can just neglect the effect of the small emitter resistance that's being added to calculate your common mode gain. Right, so with this resistor here, we have some degeneration going on, and 1 plus GM REE, if REE is much larger value, the 1 will cancel, the transconductances will cancel, and we will be left with RC over 2 times REE. In the ideal case, our common mode output will be 0, but there is typically some differences in your components, and only the collector resistor can affect our common mode gain for our fully differential configuration. So a change in, or a difference in the collector resistors will be our common mode gain for fully differential. So a difference of 200 ohms, this will be 1 millivolt per volt for a 100 kilo ohm resistor being used, and 12.2 millivolts per volts for a 8.2 kilo ohm resistor being used. And this is when we are using a resistor bias and not a current source. Right, so for single-ended, the RC over 2 times RE is our common mode gain, since they can't be subtracted from one another. And that brings us that we have a larger common mode gain for a current source, and a much larger one when using our resistor bias. Alright, now BJTs have some defects as well, just like our MOSFETs had. And one of the things that can go wrong in our circuits is that our collector resistors are different sizes. And for our transistor itself is that its saturation current is different. Now this IS is due to the area of your transistor. So if the areas of the two BJTs differ, there will be a difference in offset voltages. So the one that's easy to demonstrate is a difference of 200 ohms. That will give us a 500 microvolt offset voltage, but we need to multiply that with our differential gain, and that will give us an offset of 100 millivolts. Okay, so if you're very familiar in electronics, when you have op amp, they have a specification of offset voltage, and this is due to mismatches inside that operational amplifier. So whether it be the differences in resistors for your differential amplifier, or the areas of your BJTs, there will be an offset voltage at the output, and that gets amplified by your differential gain. So you should always cater for offset voltages when doing your feedback circuits or your external circuitry to one of these amplifiers. Right. We also get offset currents for our BJTs. So typically the current flowing into the two bases. So for NPNs, it's flowing inwards. If it's PNPs, they will be flowing outwards. They need to be the same, because if we have matched transistors, they need to be equivalent. So the bias currents is I over 2, so 1 milliampere divided by 2 divided by beta plus 1 will give us your bias current. In a practical situation, they will not be equal to one another. So you will find that there is typically a bias current in the description, and that is just IB1 plus IB2 divided by 2. So this is just the average of the two bias currents. Right. So these two can be different. That is our mismatches of our beta values. So our offset current is our average base current multiplied by the percentage difference in our base, in our beta value. Okay, your offset current is also when you take the absolute value and subtract the two bias currents from one another. Right, so you always need to cater for these offsets um, while you're working with a BJT based differential amplifier. So, in summary, before we go to our simulations, our differential gain for a fully differential amplifier is GMRC. Our common mode is dependent on differences between these resistors, so it's delta RC over 2 times REE inverted. And it's only dependent on the changes in our collector resistor here. Um, sorry, I removed the one that was here in between. It was left over from a different presentation. Our output impedance will be 2 times our collector resistors, and our input differential impedance is 2 times R pi. And again, the common mode rejection ratio is our differential gain divided by our common mode gain absolute 20 log thereof. If we were to include emitter resistors, our gain will be degenerated, but our input impedance will be increased by 2 times beta plus 1 times RE. For our single-ended, so we threw away this RC value over here. It is not needed in this amplifier. This is our non-inverting terminal. This is our inverting terminal. And our output is taken right here. Our gain will be half. Our common mode will be dependent on our emitter resistance down here, and our output impedance will be 1 times RC when looking in. Our input impedance will still be 2R pi, and note that we have the same kind of increase when we add emitter resistors. And for the gain, when adding emitter resistors, it is degenerated, and we will have half the gain, just like we had with the one without emitter resistors. Okay, so in short, you can treat these amplifiers the same in your mind as common emitter amplifiers, and from there you can see what your gain is. If it's just one output, you know that you need to take half of the output. Right. Same with the emitter resistor being added. And your input impedance needs to be double. So, very, very similar to the common emitter amplifier. Right, let's go have a look at our simulations. Our first simulation is the DC bias, so we ground it with two inputs, and let's see what we get. So 1 milliampere current source, 500 micros flowing on both sides, very close to 5 volts at the collectors, and for the 2N quad 2 transistor, it's not quite 0.7 volts, it is closer to 0.6 volts. But yeah, so typically you will use the estimate of 0.7, but for some transistors it is sometimes more, sometimes less. 0.7 is a good guess to make. Okay, so our emitter voltage here at minus 0.6 volts. That is our circuit DC. Our common mode with a 1% mismatch in the component, 2 volts peak to peak input. If we run this, here we have our two outputs, and there is a slight offset between them. So if we take the differential or our actual output here, we have the difference between these two nodes. Note that we have a 100 millivolt offset due to our collector resistors mismatching, and our difference between the two peaks here is minus 1.67 millivolts. So this will boil down to what? 0.8 millivolts, which is fairly close to the 1 millivolt per volt that we had in our calculations. Okay, so that is the common mode with mismatches. Let's match these two components quickly. And if we run this, we will see that there is no offset and no signal running. If we look at just one side, there is a signal, other side there is equivalent signal on this collector voltage right here. Okay, so perfect matching of components, there will be no common mode signal entering or leaving our amplifier. So our differential mode, I put a 20 millivolt signal in on the one side, and if we run this, we should be seeing half the gain sitting on this side, half the gain sitting out of phase on that side. So if we take the differential like this, our input is 20 millivolts and our output goes to plus minus 4 volts, which confirms our 200 volt per volt gain. If we look at this just on the one side, that is half the gain that we have here. Right, so 20 milli in, let's up this a bit, let's make it 40. And we can see that we can start to go to our rails, but there is a little bit of distortion on our signal already because we are driving our transistors with too large a signal, and to fix that you need to add some emitter resistors. Okay, so our gain is already decreasing due to our inputs being too large. Right, so that is one of the problems that we have with using the BJTs here. Next is our common mode with a resistor bias. So if we take a look here, we have at 0.6 volts per volts again, same as the MOSFETs that we had for using a resistor here. And if we do our differential, we will see that we have our 100 millivolt offset, and we have a fairly large common mode signal as well. So 21.5, that is 10.7 millivolts per volts. Common mode signal right there. Okay, so using resistors for single-ended is bad. Using them in differential mode, you will get the offset that you need to cater for, and you will get a common mode signal, but it is not that large as a single-ended output. Right, here we have a resistor with differential mode input. So the differential will be the same. Nothing strange will happen. Only thing that I can think of to do here is to prove our input and output impedance at this point. So where is our differential output? 2 volts peak, 10 millivolt peak input, so that is 200 volts per volts gain. Now if we make this 20 kilo ohms, our gain should be half. There it is, 1 volt. And our input impedance was calculated for this to be about 20 kilo ohms. So I place a resistor here and make it 20 Ks. We have a problem. Okay, due to the nature of our amplifiers having bias currents that needs to enter, having the resistor just on one side like this will cause a problem for us. We will get some offsets with it. So if you want to place a resistor here, it is best to split the resistor between the two inputs like that to have some form of balance. Okay, there the two currents will be falling on top of one another. And now if we do the differential, it will be in the middle and our gain is halved. Okay, so our input impedance is 20 kilo ohms. Our output impedance is 20 kilo ohms for fully differential right here. Right, and that is our differential mode. Right, here is a single-ended conversion. And as you see, I'm not even catering for the offsets, but you will see that there is a bit of a mismatch. 10K on the out, 10K here, 20K on the input, and our gain is half, half, and halved. Okay, so 200 became 100, became 500 milli out. Sorry, 20 millivolts times 100, which is half the gain, is 2 volts. If we half that, is 1 volt on the output. If you half that due to the input impedance, it is in the range of 500 millivolts. Okay, so the single-ended, we lose half our gain as well. If you want to improve this again, cater for the bias currents, and there we will have our full half a volt output from our 20 millivolts like that. So always cater for your offsets. These two will now be more or less on top of one another. Okay, so that is our single-ended conversion. Next is where we add some emitter resistors. And the task here is to prove that our output impedance is the same, our gain gets reduced, and our input impedance is now 60 kilo ohms. Note that I split it between the two halves. Okay, so 20 milli in times 200 is what, 4 volts. Half the output should be 1 volt in the end. And I made a boo-boo, or did I? I didn't. I forgot to include the effect of our emitter resistors. So, with our emitter resistors, our gain is 67 volts per volts for our differential or our fully differential output. So 20 millivolts in multiplied by 200 degenerated by 1 plus the transconductance of our emitter resistor times half for the output loading and half for the input impedance being the same as the source, and that gives us 350 millivolts, like that. So if we make this 20 megs, our output should double. If we get rid of these two resistors, our output should double, and we should see that we are on 67 volts per volts. So 20 milli times 67 is our little bit more than 1.2 volts that we see here. Right, which is what, 1.34-ish, around there. So degeneration, but we saw a larger input impedance, output impedance remained the same. Our last simulation is the single inlet conversion, and we are using a 8.2 kilo ohm bias resistor. So if we run this, we see that we have 20 milli going in, and this gets split between our two inputs. I used matched input resistor, so this is a 60 kilo ohm. A little bit of a mismatch due to the removal of our collector resistor right here, but our bias currents are in a similar range. And if we take 20 millivolts peak multiplied by 53, which is the gain, and then half due to the input loading and half due to the matched output, we get 165 millivolts peak output right here. So that confirms our 53 volts per volts gain for this amplifier. That's excluding our loading effects. So yeah, there is the single-ended conversion, and that is it on the basic BJT differential amplifiers. So yeah, thank you for watching, and see you in the next video.